formal powers, or you can actually let them act on other functions as well, but let's stick to polynomials for now. We have the operation of differentiation and the operation of multiplication by x. Then one thing one can maybe observe is that these two operations do not commute. If I apply du to a function, a polynomial f, let's say, then, well, I multiply by x first, so u gets applied first, I get x dfx, and then I differentiate, which by the product rule gives me f of x plus x f prime of x. If, on the other hand, I start with d, differentiation, then multiply by x, then I'm just getting x f prime without this additional f. So the two operations do not commute. It makes a difference whether I differentiate first or multiply by x first. And I can combine these two into one equation, which says du minus ud applied to f is just equal to f. So du minus ud is the identity operator on polynomials, but also on other functions. So we can write this as the relation du minus ud is equal to 1. And that's really the defining property of the Weyl algebra from an abstract point of view. But if you don't want to talk about abstract algebras, I think for the rest of your talk, you will be absolutely fine by just thinking of d as differentiation and u as multiplication by x, and no abstract algebra is required at all. But if you do want to think about it on a more abstract level, then you can actually think of this as an algebra. So an algebra is a structure that's kind of both a ring and a module. It's got the two generators d and u, and the relation that I've just derived, du minus ud, is the defining feature of the algebra. So that's what kind of distinguishes it from the free algebra, where d and u just do not commute and there are no further relations at all. So it turns out that using this relation, you can actually write every element in terms of a standard basis of the form d to the I, u to the j. So everything can be expressed as powers of d times powers of u, or also the other way around, the way you prefer it. So for example, if I want to express UDDU that way, I can split it into ud and du. Then I can say that ud here is the same as du minus 1. Multiply out, and I'm getting du minus du. I've got another ud hidden in there. I can do the same thing again. The ud becomes du minus 1. And after multiplying out, I end up with d squared u squared minus 2 du. If I do the same with du ud, then it turns out that I get the exact same expression. I can follow the same steps as before, so I split into du and ud. By the defining relation, I can turn ud into du minus 1. It becomes again du minus du, and the rest of the steps is the same as before. So UDDU is the same as DUUD. If you think of differentiation and multiplication by x, what it says is if you multiply by x, differentiate twice, and multiply by x again, you get the same thing that you would also get if you differentiate, multiply by x twice, and differentiate again. You can try it out. It's not too hard to convince yourself that this actually works. So we have the relation UDDU is DUUD. And that's really where the questions start. So we have a non-trivial identity of two things in this algebra. And we might be interested in what other identities hold, how we decide whether a certain identity holds. And then, because we want to do enumerative combinatorics, we want to count things. So we might want to count how many different, in the sense of this, words are there of a given length. How many words are equivalent to a given word? Things like that. Right, so these are the questions that I will be interested in the rest of my talk. So how can we characterize such monomial identities? UDDU equals DUUD is one of them, but there will certainly be more. How do we characterize them? How can we decide, given two monomials, with a reasonably efficient algorithm, whether they are actually equal, so whether they represent the same thing in this Weyl algebra? If we consider this equality as an equivalence relation for UD words, length n, how many equivalence classes do we have? So, of course, if I consider words of length n, there are 2 to the n many words, but now some of them will be equivalent. For example, the two words UDDU and DUUD. So we might be interested in the number of equivalence classes, which will then have to be less than this 2 to the n. Or given a specific word with the letters U and D, what's the size of the equivalence class? And I will try to answer these questions today. There is a nice connection to lattice paths. And so the use of the two letters D and U is somewhat suggestive as well. I can interpret words with the letters D and U as lattice paths, and I will call them diagonal paths in the following, because everything is represented by diagonals. U stands for up, like here, and the D stands for down, like this one. So the example that I've drawn here corresponds to the word UDU, UDDD. Up, down, 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 down. So I have, for every word, a path that corresponds to it. If I fix the starting point, that will usually be the point 0, 0. Then I have a unique path that corresponds to each word with the letters D and U. I need a couple more definitions about these lattice paths. So for such a path P, a diagonal path of length K with the vertices P0 up to Pk, the NE steps, northeast steps, are the steps that go up. And I identify the steps with the vertices where they start. So I say the vertex Pi, where it goes up, that's an NE step, northeast. The southeast steps is the vertices where it goes down after that. And finally, I have this notion of height. The height is simply the y-coordinate. So the initial height of the path will be the y-coordinate of the point at the beginning. The final height is the height of the point at the end. We usually take the initial height to be 0, and the final height, well, will depend on what exactly the path is. So in this particular path, so my P0 is here at the beginning, P7 is at the end. This is a path of length 7 with 7 steps. In this example, the northeast steps are at P0, P2, P3. I've got 3 of them. The southeast steps are exactly the other ones, so P1, P4, P6, P7, P5, P4, P5, P6. That's the southeast steps. And the initial height, if that is 0, then the final height in this example would be -1. Okay. We'll need these to state a couple of things. Now, why is this lattice path representation actually useful in our context? That should become clear, hopefully, with the following proposition, which directly relates what a UD word interpreted as an operator acting on polynomials, what it does to a particular power x to the s. Right? So every UD word can be interpreted as an operator that is acting on polynomials. So you can ask what it does to a power x to the s. And it turns out that you can express this quite neatly in terms of the path that represents the given word. Namely, the result, the outcome, if you apply W interpreted as an operator, as an element of the Weyl algebra to x to the s, is x to the some power, which is s plus the height difference, basically. And then a factor, which is a polynomial in S. So each of the linear factors here has S plus the height difference between HK, that's the final height, and the height following a down step, an SE step. Okay, so if PI is an SE step, then the point that comes after the down step is the I plus 1th. Its height is HI plus 1. That's the term here. So what this represents here is the height difference between the end and what comes right after a down step. For each down step, there is one factor in this product. So the whole factor here is a polynomial in S, and then I've got x to some power. At least, so the part at the end is not too hard to explain, because with every up, you multiply by x, so you increase the exponent by 1. With every down, you differentiate, which decreases the exponent by 1 and also produces a factor, but it in particular decreases the exponent by 1. So the total change in the exponent is simply the difference between the height at the end and the height at the beginning. And that's exactly this hk minus h naught. And then every time you differentiate, you gain a factor. And this factor is simply the exponent at that particular point, so which is s plus however the height has changed up to that. And this can be expressed like this. I'll also show you in an example. If I have a UD word that ends with DUUD, then last steps in my path are down, up, up, down. If I apply to a power x to the s, then, well, the first step is to apply d, because it's the rightmost thing. That gets applied to x to the s right away. It gives me s x to the s minus 1. Then I multiply by x twice, so I get x to the s, then x to the s plus 1, and then I differentiate again, giving me a factor x s plus 1, and the exponent goes back to x to the s. So I've got s plus 1, x to the s. And the two factors s and s plus 1 correspond exactly to the two times when I went down. That was here and here. That was the two d's. They correspond to the southeast steps, the down steps. So each time I do differentiate, I gain a factor, and, well, you just have to figure out what comes here after the s plus, and that is exactly this height difference. So it's not too difficult to prove this proposition. You can do it by induction, for example, but it's very useful for us because it characterizes exactly what our words, regarded as operators, what they do to powers of x. And so two things are equal as operators if they have the same effect on all powers of x. So we can also use this proposition to characterize equivalence at the end of the day. Right, so as a consequence of this formula, we can say that two words that are represented by two different paths, P and Q, starting at the same initial height, are equivalent if and only if, first of all, they have the same final height, because otherwise the exponents don't agree. And also, I need that the heights at the southeast step or the northeast steps, they must be the same. The two turn out to be equivalent, actually. So you can take the northeast steps or the southeast steps, and it will amount to the same thing. In particular, P and Q will have to have the same number of northeast steps and the same number of southeast steps for the equivalence to hold. Right. For some further characterizations, we need a few more notions. So specifically, we'll talk about balanced words. A word is said to be balanced if it has the same number of D's and U's. so that in the corresponding path, the final height is the same as the initial height. You go as many times up as you go down. Then from our proposition, it follows, as we saw, that for a balanced word, the exponent at the end is the same as at the beginning. And I gain some factor that depends on the word, but is a polynomial in S, certainly. Now, if I apply two such words in a row, then the polynomial in S being sort of a constant can be factored out. And for any two balanced words, W1 and W2, if I apply them in order to x to the s, then actually the order doesn't matter, because when I apply the first one, W2, I'm getting some constant that depends on s times x to the s. And then applying W1, that constant can be factored out. And the effect of applying W1 is simply that we are getting a factor PW1 of S. But here it didn't matter in which order we did it. It would make a difference if they weren't balanced, because then after applying one of the operators, I'm not back to the same exponent. So when I then apply the other operator, I get the polynomial associated with that operator, but with a different S plugged in. So this only works for balanced words. But we make the important observation that balanced words commute in our algebra. And a typical example of balanced words are the words UD and DU. Obviously, they have a D and a U each. So we found now that they commute. I can exchange DU and UD, which is one explanation of why DU UD is the same as UDDU. We'll find other explanations for that as well. So based on this observation, we define an equivalence relation on words. So we say that two words V and W, they are obtained from each other by balanced commutation, if and only if we can write them as something, then some balanced word X, some balanced word Y, and then something else. And then we swap the two balanced words inside. So I just replace the order of xy by yx. It is called a balanced commutation. Because we have seen in the Weyl algebra that's sort of a permissible operation. I can interchange the order without changing the effect. So if we iterate this, if we are allowed to apply balanced commutations repeatedly, then we get an equivalence relation that is denoted by this tilde bal for balance. So two words, V and W, are equivalent according to this if I can transform them into each other by a sequence of such balanced commutations. So here I have indicated the balanced commutations that are taking place with red and blue over and underlined subwords. So DU is balanced, DDUU is also balanced. So I'm allowed to interchange them, which I've done here. This new word has also the balanced subwords DU and UD over here at the end. So I can also exchange this, meaning that my original word DU, DDU, DU, UD is balance equivalent to the word at the end, DDU, UDU, UDDU. I can do this as often as I want. Any two words that I can transform into each other by such operations are called balance equivalent. So they are denoted by this equivalence sign. Now it is clear that two such balanced equivalent words are equivalent in the Weyl algebra, because we have observed that this interchanging the order of balanced words has no effect. It's not entirely clear whether that's the only reason for two words to be equivalent, but we will actually see that the converse holds as well. So two words are only equivalent if I can perform such a sequence of balanced commutations. A second operation that's kind of similar is balanced flips. So for a word x, I say that omega x is obtained by reversing the order and also replacing every u by d and every d by u. We call this toggling. So for example, if I take UDDU, I replace every du by d and every d by u, I would get duu, but I'm also reversing the order, so it becomes uud. Now on the level of paths, what does this mean? Well, exchanging the order and also replacing these by u's and u's by d's is exactly reflection with respect to a vertical axis. Right? So if you reflect with respect to vertical axis, the up steps become down steps and the other way around. And also you're changing the order. Left to right becomes right to left. So for a balanced word, the multiset of northeast steps or the multiset of southeast steps is unaffected by this reflection, because if a word is balanced, then the corresponding path has to start and end at the same level. So then it's pretty clear that at every level you have to go up as many times as you go down. So when you reflect, that's still the case. You're going up as many times as you're going down on every level. So the number of up steps and the number of down steps on every level stays the same. And this means that when you do this balanced flip, this multiset stays the same, but we actually saw that this multiset characterizes what happens when you apply a word as an operator to x to the s. So we can make the observation that if x is balanced, then x and this omega x are equivalent in the Weyl algebra. And an example of this would again be DUUD. If you exchange these by u's and u's by d's and reflect, which actually has no effect because it's symmetric, then you get UDDU. So again, a reason why UDDU is the same as DUUD. You can argue by this what we call balanced flip. So I'm again allowed to iterate this. So if I take two words, V and W, I say that V is obtained from W by a balanced flip, which means performing the flip that I just explained on the previous slide on a balanced word somewhere inside. So if I can express V as px cubed for some balanced word x, and then apply this omega to x, then I'm getting a new word, and that is what I call a balanced flip. Again, I define an equivalence relation based on this, where I say the two words are equivalent if I can transform them into each other by a sequence of such flips. So for example, DUDDUU could become DDUUDU by one such flip. And I could repeat this now with a different balanced subword. In this particular case, I don't think I would be able to do very much further, but if there is a longer word, then of course you can flip something else still. So again, by what I've discussed, it should be clear that two words that are, this should be flip here, not balanced. There is a typo here. Two words are equivalent in the Weyl algebra if I can obtain them by these balanced flips. Because one such balanced flip, as I explained, doesn't change anything. So repeated application also doesn't change anything if I consider the words as operators. And again, the converse of this holds as well. So this is an if and only if, as we will see. Right. So the last set of definitions is about height polynomials. So for a diagonal path, I associate a height polynomial, which simply just collects the height of all the vertices, makes them exponents. And two subvariants of this are the northeast height polynomial, where I only take the northeast steps and record their heights as exponents in my polynomial, and the southeast height polynomial, where I do the same, but with the southeast steps. So for every point on my path, for every lattice point, I take the height in the first case, and then make this the exponent in a monomial, and then I just add all these. Right. I have this equivalence of multisets if and only if the corresponding northeast height polynomials are the same. That's sort of clear from the definition. But actually, I have this equality as multisets even if any other polynomial agrees on the two paths P and Q. And that's because of this lemma here. If I have two diagonal paths that start and end at the same height, then actually I can express one of the height polynomials in terms of the others. So the first height polynomial, where I record all the steps, can be expressed in terms of the northeast height polynomial. It can also be expressed in terms of the southeast height polynomial. And so one of these three polynomials is uniquely determined by the other two. I can always sort of convert between any two of these three polynomials. I have some infinite series here, but these are really just formally infinite because all but finitely many terms cancel when I take this difference. Right, so if two paths start and end at the same heights, then if they agree on any one of these three polynomials, then they agree on all of them. Because I can convert from one polynomial to the other two. All right, so we are now getting to the main sort of characterization result of equivalence in this Weyl algebra. If I take any two UD words and the two corresponding paths that are called P and Q, I make both of them have initial height 0, then all of the following statements are equivalent. So the two words are equivalent in the Weyl algebra. So this is in an algebraic sense. If I take the abstract algebra that's defined by the generators U and D, and the relation UD minus DU is 1, then equivalence, then that's equivalence in the Weyl algebra. Equivalence in the sense that by so applying this relation, they would have the same basis representation, for example. This is equivalent to the words acting the same way on polynomials. The equivalence of the first two was known long before us, so this is not new. So the characterization of this equivalence in terms of paths is the first item that's new and relevant for us. So the words are equivalent if the corresponding paths have the same final height, as well as initial height, of course, by definition, and the height polynomials are the same. And this works with any of the height polynomials. I can take the northeast height polynomials, I can take the southeast height polynomials, and there is again a typo, but you didn't notice it. Well, this should be P and Q, not U and V, but otherwise it's the same statement as here. So the northeast polynomials agree, the southeast polynomials agree, and also the paths, the just general height polynomials agree. All of these are equivalent by the lemma before, but they're also equivalent to this. So equivalent is that U and V can be obtained from each other by balanced commutations. Also equivalent is that they can be obtained from each other by balanced flips. So all these 7 statements ultimately are equivalent to each other. So I can characterize really well what it means to be equivalent in the Weyl algebra. If you give me any 2 words, then I can decide quite easily based on this path characterization in particular whether they are equivalent or not. One thing that will be useful then for our enumerative questions is what is called the abnormal form. We called it the abnormal form. So we can now group words into equivalence classes. And it's useful to have an element of each equivalence class that is in a sense canonical. And that's what the abnormal form does for us. I need to define what that is. So I call a word rising if it has at least as many U's as D's. So in terms of the path, that would mean it ends on the x-axis or higher. A downzig is a word of the form u, then a couple of d's, at least two, and another u. So up a number of times down, up. And a rising word is said to be abnormal if it doesn't contain such a downzig. So for example, UUDU, DUDD is abnormal in this sense because there is no subsequence of the form u, more than one d, and another u. So the d's are only allowed to stand alone, except perhaps at the beginning and at the end. Like here at the end, there are two d's in a row. This is allowed because there are no u's sort of around them. But inside, I can only have single d's, like here and here. The rising word UUDDUU is not, because it contains this downzig UDDU. Yeah, the canonical representative of each equivalence class, as it turns out, is exactly this abnormal word. So if I take any rising word, then there exists a unique abnormal word that is equivalent in the sense of this balanced commutations. And it has this general shape, a number of d's, then some ud a number of times, again a u, ud a number of times, again a u, and so forth. This is a canonical way of writing them. In terms of the path, this must mean going down for a while, then zigzagging for a while, going up one step, zigzagging for a while, going up one step, and so forth. At the end, after the final up, you go down for a number of steps again. The main idea of the proof here is that if a word is not abnormal, then there is a downzig somewhere, and you can apply some balanced commutation that will transform the word into something that's lexicographically smaller. And then the lexicographically smallest word is necessarily the abnormal representative. Okay, so now we finally get to the enumeration. We're interested in the number of equivalence classes. So A and K will be the number of equivalence classes of words with KDs and N minus KUs. One obvious property is that AN0 equals ANN equals 1. That's the cases where you only have U's or only D's. In this case, that's the only element of the equivalence class. That is fairly easy to see because you can't perform any balanced commutations, any balanced flips, nothing like that. And you also have this general symmetry, A and K is equal to A and N minus K. So if you replace the number of D's by the number of U's and vice versa, you get the same number of words in your equivalence class. One way to prove this is by using the reflection on the associated standard paths, because that will turn U's into D's and vice versa. Right. So for enumeration, we will rely in particular on the following recursion. This holds whenever there are more U's than D's. So I'm considering rising words. I need N greater than 2K. So K, to remind you, is the number of D's. So if N is greater than 2Ks, it means I have more U's than D's. In this case, I can recursively determine A and K from two other values of AN minus 1K and AN minus 2K minus 1. This is represented as 0 if K is 0. In all other cases, this is still well defined in that N minus 1, N minus 2 are still non-negative. How do I prove this recursion? Well, I apply a bijective argument to the abnormal representative. Each equivalence class can be identified with its unique abnormal representative. So A and K just counts the abnormal words with KDs and N minus KUs. And then there are basically just two cases, two types. An abnormal rising word could be a word where the corresponding path has only one vertex at maximum height. Then, and I'll show you a figure in a moment, I remove the last U. That gives me a bijection with classes counted by AN minus 1K. steps by 1, so n minus 1, but the number of Ds is still the same, it's still k. And the other possibility is that the corresponding path has at least 2 distinct vertices where the height is maximum. Then I remove the last u and the d that comes right before it, and I obtain a bijection with classes counted by this. I remove 2 elements, so n minus 2, and one of them is a d, so k minus 1. Here is an illustration of the bijection in a special case. This is the first type. So my path drawn here has only one vertex at maximum height here at the end. That's the red. That's the peak of the red arrow. So I remove the last u, which means to this final peak. And then I get a shorter path that already goes down here. But this still corresponds to an abnormal word, as you can convince yourself, and it represents a bijection. You can also go back from any abnormal word. You can just insert a u before the final sequence of Ds. And for words of the second type, it looks like this. Here you see that I have 2 peaks at maximum height, here and here. And what I do is I replace the final u and the d that comes before it, and just shift the rest here to the left. And again, you can convince yourself that this results in an abnormal word, removing this final du, and that it represents a bijection. So this proves our recursion, which together with the following lemma actually already characterizes the sequence ANK, or the array ANK completely. So A2KK would be the number of words in the equivalence class where you have k, ds, and kus. So that's exactly the balanced words. Here it turns out that the number is k plus 3 times 2 to the k minus 2. This is again by considering abnormal words. You just have to count how many abnormal words you get with the more or less applies here. You have k many ds and k plus 1 many u's, and again you count how many abnormal words you get. Once you have these formulas and the recursion, ANK is completely determined. So one thing you can, for example, do now is to derive generating functions. There are 2 possibilities you can use for the generating functions. This one is where you include all the ANKs. Here is where you only include the ANKs which have at least as many u's as these. So only the rising words. Gives something slightly different, but still rather similar. Both of these generating function identities follow by applying the recursion and the formulas I've just shown you. Moreover, you can actually give a rather neat explicit formula for ANK. ANK is given by this sum. Some factors and binomial coefficients, nothing out of the ordinary. It's easy to produce a table based on this formula, which I've done here. So this is ANK for n up to 7 and also k up to 7. Of course, you see the symmetry in each row that we have observed before. So ANK is the same as AN n minus k. As a corollary, if you sum overall values of k, you also get the total number of equivalence classes, which has a somewhat surprising looking formula. The total number of equivalence classes for length n can be expressed in terms of the Fibonacci sequence and powers of 2. There is a slight difference depending on whether n is even or odd. But you have this completely explicit formula otherwise, allowing you to produce the sequence. And yeah, here is a table showing the numbers. Words of length 0, there is only one, that's the empty word. there are 2 words of length 1, 4 words of length 2, 8 words of length 3. The first interesting case is length 4, where it's not 16 anymore, because we have the equivalence of UDDU and DUUD. That's the first time that 2 different words are actually equivalent when we have length 4. So they're not 16 equivalence classes, but only 15. With length 5, there would be 32 words, but only 28 equivalence classes at the end of the day, and so on. Now, one can modify these questions in a number of ways. So one particular question that was, as all of the other questions in here really raised by Richard Stanley, is if you take words with the restriction that every prefix has at least C times as many U's as D's. So if you know DUUD paths, those are paths that have to stay above the x-axis. So every prefix has to contain at least as many ups as downs. And this is a slight generalization where you take an arbitrary constant C and you need at least C times as many U's as D's in every prefix. And then if you count equivalence classes with this restriction, you get a new type of sequence ACNK. And even in that case, there turns out to be a very nice explicit formula. Looks like this. So specifically when C is 2, everything cancels out nicely and you just get binomial coefficients, which is perhaps surprising. But there is also a bijective explanation for why it holds in that case. The final enumerative question is, if you give me a word, how many words are equivalent to it? So what's the size of the equivalence class? And this can be described in terms of these height polynomials again. So if you know the height polynomials, height polynomial associated with the path corresponds to a word, then you can say exactly how many words are equivalent to your given word, and you can express it as a product of binomial coefficients, basically. There are 3 different cases, depending whether W is balanced or rising or falling. Falling means, so the opposite of rising has more D's than U's. So the number of equivalence classes also has an explicit formula. And let me conclude. There would be other interesting connections. There is more, and you can look it up in our paper if you want to. Connections to other topics such as Rook polynomials and Rook theory, if you know what that is. So basically, you can interpret certain tables as chessboards and then place rooks on the chessboard, and you have to do this in such a way that they don't attack each other, and this gives rise to something called Rook polynomials. Another connection is to something probabilistic called bond percolation. So there is a way to relate things in some way to that as well. And lastly, a bit of an outlook. So what else could one do with all of this? We've got this characterization. We've got a number of enumerative results. But this was, of course, just one rather special algebraic structure, the Weyl algebra. There are, of course, many other similar structures and other, in particular, other algebras where it would certainly be equally interesting to study similar questions. In here, we have always been taking the algebra over the field of reals, or maybe complex numbers, for example. How do things change if you're not doing that, but working in characteristic P? What if you take an algebra that has a different set of relations? So in our case, the defining relation was DUD minus DU equal to 1. But you could take other relations and define algebras based on that. And this has, of course, been done. Many other types of algebras have been studied. And it would certainly be interesting and natural to study similar questions for other algebraic structures like those. So yeah, with this little outlook, I thank you very much for having me. It's been a pleasure to speak in this seminar, and I look forward to any questions you might have.